In this video, we're going to look at Unit 7, Lesson 4, which is quadrilaterals in circles. So let's go ahead and investigate quadrilaterals that fit inside of a circle. So by the end of this lesson or the end of this video, you will be able to determine missing angles in a cyclic quadrilateral. All right, so let's take a look here. For this activity in your book, it starts on page 165. Go ahead and try to draw a circle around each of these three quadrilaterals that will touch all four vertices. So one circle that'll go through all four vertices. Give it a shot, then come back to the video. All right, so hopefully you had some time and looked at drawing circles around here. Which shape was the easiest for you to get a circle drawn around? And maybe that was the square, because it kind of, you could almost look for the center right in the actual middle of the square and then draw your circle. Maybe you hopefully got one around this trapezoid as well. And then was there any shape that you couldn't draw the circle for? So maybe this C, you couldn't actually find one. And we'll look into why that is throughout the lesson. So what this is called when we draw a circle around a shape like this and it hits each of the vertices, this is called circumscribing a circle. Okay, so circum meaning outer. Okay, so outside, we can draw a circle outside of a figure. And so all of the vertices on this figure are touching the circle. So the circle is said to be circumscribed around that pentagon. And then the pentagon is said to be inscribed inside of the circle. So circumscribed is the outer figure and inscribed is the inner figure. Then also when you can do this to a quadrilateral, this quadrilateral is actually called a cyclic quadrilateral. So a cyclic quadrilateral is one in which you can circumscribe a circle around it. So we can draw a circle that will hit all these vertices at the same time. That's what a cyclic quadrilateral is. So let's go ahead and look at these three cyclic quadrilaterals. So we see them drawn inside of a circle. Go ahead and highlight the arc from S to Q that passes through P in each of the pictures. So you want to go S to Q and make sure you go through P. So highlight that arc. Then find the measure of your highlighted arc. Find the measure of the other arc from S to P. And then find angle SPQ. So go ahead and do that and then come back to the video. All right, so here is if we highlighted each of those arcs. And so let's go ahead and find the measure of each of these arcs. So hopefully you see them connected to this angle. Let me just draw this with an actual segment here. So we see that the end point of this arc goes into this inscribed angle here. Okay, we can also see it here in the next one and whoops. And again in this one. All right, so then that'll help us get the arc measure. So remember that an inscribed angle is always equal to half of its intercepted arc. So if we have the angle, we can just multiply it by 2 to get the size of the arc. So 105 times 2 gave us 210. 62 times 2 gives us 124. 130 times 2 gives us 260. Then we were supposed to find the measure of the other arc from S to Q. So if we take a look, so now we want this one. And so if we're coming up with the measure of that arc, remember the total of a circle is 360. So we should be able to do 360 minus 210 and get the remaining portion of the arc. So in this case, 150 degrees. For this one, we can do 360 minus 124, and we would get 236 degrees. And for this final one, 360 minus 260. So we would get 100 for that remaining arc. And then our last thing that we were supposed to do here was to determine this angle. So angle QPS, which is the inscribed angle of this arc that we just found. And so we should be able to take the arc and divide it by 2 to get this angle of 75 for this first one. QPS here again intercepts that 236 degree arc. So divide that by 2 and we will get 118 degrees. And then this final one is intercepting the 100 degree arc. So divided by 2 should give us 50 degrees for that angle. All right, then in the next problem, it gives you a diagram like this, and it asks you, now that you've kind of looked at a couple of these, could you determine what the total of alpha and beta, these angles across from each other, what do they add up to? So what is alpha plus beta? So maybe go look back into these examples and see what the sum is here and notice if it's the same in each case. So let's take a look. And so in this first one, when you did 75 plus 150, or sorry, plus 105, we get 180 degrees there for the sum. 62 plus 118 gives us 180 for this sum as well. And then 30 plus 50 is again 180. So we're seeing in each of these cases that we're getting 180 degrees for those angles across from each other. So it would stand to reason that the two angles across from each other like this are equal to 180 degrees. And could we think about why that happens? So if we're thinking about this arc here to here, so this arc is giving us this beta, okay, so half of this arc. And then this other arc, half of it is giving us alpha. And these two arcs, okay, so this smaller arc plus this bigger arc are the total of the whole circle, which is 360. So if we take and divide these arcs by 2 and add them together, it would stand to reason that we are always going to get 180 degrees for those angles across from each other in a cyclic quadrilateral or a quadrilateral drawn into a circle. And the term, do we remember the term for if two angles add up to 180 degrees? So a term for that would be supplementary. So is there a special name for angles with that sum? So we got 180 degrees for that sum, and angles that total 180, we remember, is called supplementary angles. So take a couple minutes to look at these pictures here. What do you notice and what do you wonder? So think about that for a couple seconds. So could notice and wonder quite a few things. Maybe you noticed those are the shapes that we just did earlier and we tried to draw circles around. And maybe you'll notice in A, we see the 90-degree angles. Okay, so we see that these are 90-degree angles. So that means that 90 plus 90 is 180. So that's following this guideline. Maybe you know that this one, C, we could not draw a circle around. And that makes sense because this angle and this angle are both obtuse. And two obtuse angles can't equal 180 degrees together. And these ones right here are both acute angles. And together, two acute angles can't equal 180 degrees either. And so maybe you wondered some different things here, like what are we could draw it around B. We could draw a circle around B when we tried. So what are these angle measures? And now that we know that the angle measures, once we have a circle drawn, have to be 180, could this go backwards? So once I know there's a circle, does that mean that they equal 180? Okay, so once we knew there was a circle around this one, does that mean that these two angles have to total 180? So those are just a couple of things that maybe you noticed and wondered in that. So let's take a look at this quadrilateral here. We're being told that it's a cyclic quadrilateral. So we know it's cyclic. That means that we can draw a circle around it. So that's going to be our goal, is to draw the circle around this quadrilateral. So we're going to start that by drawing diagonal BD, then constructing the center for the circle, then drawing the circle, and then thinking about, can we do this for any cyclic quadrilateral? So on page 168, why don't you go ahead and give it a try? And then you can come back to the video and I'll walk you through it. All right, so we're going to draw in diagonal BD here. And what do we know about that segment in regards to the circle that we're trying to draw right now? So hopefully we realize that BD is the diameter. And why is it the diameter? So it has to be a diameter since this is a 90-degree angle. And remember, a cyclic quadrilateral, all these vertices will touch the edge of the circle. So this is going to be an inscribed angle. So it is going to open up to a 180-degree arc, which will force B to be our diameter. And why is that a big deal? That's a big deal because we want to construct the center of this circle. Well, the center of the circle is going to be the midpoint or the middle of this diameter. So we're going to go ahead and construct the midpoint. So remember, to construct a midpoint, we're going to do basically the construction for a perpendicular bisector. So I'm just going to open to wider than halfway, draw a couple arcs. Okay, and I just need them to cross each other, so I'm not going to draw the whole thing. And then I'll go and do this one. So I just need to figure out where these cross. Then I'm going to draw in the perpendicular bisector, but I'm going to draw it light because we're not going to leave it. Because all we're looking for is the center of that circle now, right? So here's the perpendicular bisector. That means that this point here is the midpoint of that segment. So that's what we're looking for. And we're going to label that point O. Then you wanted to draw your circle around this quadrilateral. So I'm going to go ahead and change colors here. So we would put the center of our compass on the center of the circle and then open as wide as we know, which would be to any vertex. And then you can go ahead and draw in your circle and notice that it will hit every point. I'm a little bit off on my center there. My compass moved a little bit, but you will notice that it hits every single point. And so we've drawn in the circle. So will this work the way that we did this with any cyclic quadrilateral? So if I just give you any cyclic quadrilateral, can you follow those steps? And the answer is no, because there was one special thing that this cyclic quadrilateral had that allowed us to just find the midpoint, and that was this 90-degree angle. Okay, so that was the 90-degree angle that allowed us to realize that that was going to be a diameter. So this will not work in all cases. All right, so then let's take a look and keep looking at the picture that you drew here of this circle, this circumscribed circle. So what do we know about the distances from A to O? And remember this middle point here is point O. So what do we know about the distances from A to O? Whoops. O to B, O to C, and O to D. What do we know about all of those? So hopefully you realize those distances are all the same since they're radii of that orange circle, so they would all be equal to each other. So in looking at this cyclic quadrilateral, or is it a cyclic quadrilateral is what we're trying to decide. So looking at this quadrilateral, would it be cyclic? And remember, cyclic means that we can draw a circle around it, hitting each vertex. So if you have a point that's the same distance away from these 4 points, there has to be a circle that would cross there because all of these would be radii of your circle. So you could start it at the center and then it should go through all 4 points at the same time. And let me just change that color so it sticks out a little bit. But so if we do know that that 4 points are the same distance away from another point, there should be a circle that goes through them, making it a cyclic quadrilateral. So keeping this idea in mind, if we're given this quadrilateral here, so each vertex of the quadrilateral represents a town, and there's a construction company planning to build a shopping mall that's the same distance, okay, same distance from each town. Claire claims this is impossible. How does she know? So if these 4 towns are the same distance from a point like this, okay, so what we're looking for is this A, right? That would be the same distance from each of the 4 points. Okay, this would have to be a cyclic quadrilateral. And what did we learn in regards to a cyclic quadrilateral and the angle measures? So remember, if it's cyclic, then opposite angles need to equal 180 degrees. And so since we have the angles here, let's look and check the opposite angles. So this one we have 108 and we have 124, and those are definitely larger than 180 together. So this is not a cyclic quadrilateral. So Claire knows it's not because the opposite angles don't add to 180. All right, then let's take a look at the lesson summary. So we said a circle is said to be circumscribed about a polygon or around a polygon if all of the vertices of that polygon land on the circle. So we see that this one here has all the vertices landing on the circle. So this is a cyclic quadrilateral versus this one is not, because G is not on the edge of the circle. So this one is not cyclic. And then remember, when we have a cyclic quadrilateral, the angles we know will total 180. This will work if we see the quadrilateral. So if we see that a quadrilateral has angles that total 180, this will be cyclic. Or if we see it drawn in a circle, then we know that they total 180 either way. So they force each other. So hopefully after watching this lesson and completing this lesson, you can prove using words or other representations properties of angles for a quadrilateral inscribed in a circle, aka a cyclic quadrilateral. You can check your understanding by doing the lesson 4 practice problems. And remember that I also have a video for that if you need some more help. And then let's take a look at the cool down. So here's the cool down. Here's that diagram we looked at the beginning of the lesson. Find the measures of angle CFE. So we want CFE, this angle here. And then also find the measure of angle DEF. So this angle here. So those are the two angles that you're looking for using your knowledge of cyclic quadrilaterals.